Welcome to AlphaNumericTricks. Today we are going to see about initial value theorem and final value theorem on Z transforms. Initial value theorem says that Z transform of f of n is equal to f of z, then f of 0 is equal to limit z tending to infinity, not n, limit z tending to infinity f of z. This is the result we have to prove that. Usually when you are doing the proof, we are taking LHS and prove the RHS value. But to prove initial value theorem and the final value theorem, we take RHS and to arrive the LHS value. Okay. So for that, first you have to write the f of z definition. What is f of z definition? So that f of z meaning is a transform of f of n, isn't it? So we have to write is a transform of f of n for this. Summation n is equal to 0 to infinity f of n into z power minus n. Okay. And here we have to expand this summation. We have to expand this. When n is equal to 0, you have f of 0, z power minus 0 becomes 1. Or you can leave as it is f of 0 alone. Plus, when you substituting n is equal to 1, you have f of 1 z power minus 1. Plus n is equal to 2, you have f of 2 z power minus 2. Plus etc. up to here infinity you have. Or you can write this to be f of 0 plus f of 1 divided by z plus f of 2 divided by z squared plus etc. up to infinity you can have. This is your f of z. We rewrite z transform of the function this way. But according to our initial value theorem, you have to take limit z tending to infinity for this function. So taking limit as z tending to infinity, f of z is equal to limit z tending to infinity. You have to take z tending to infinity for all the each and every term in this summation. Okay, so we rewrite this term to be like this. Plus etc. up to infinity. When you taking limit z tending to infinity f of 0 plus limit z tending to infinity f of 1 by z plus etc. up to infinity, you have to write it, isn't it? And here there is no z term, so rewriting this, this limit z tending to infinity f of 0, which is meaningless, or you can write simply f of 0 itself, because there is no z in this function f of 0. Plus, when you substituting z is equal to infinity here, f of 1 by infinity. F of 1 by infinity, any term by infinity is 0, because suppose x divided by infinity is there. When you substituting, what is infinity? Infinity is 1 by 0. 0 goes to numerator. So x into 0 divided by 1 are 0. You get the value 0. So this term becomes 0 plus another term becomes 0 plus etc. up to all the terms. So final result we achieve is f of 0 only. So limit z tending to infinity f of z is equal to f of 0. This is our initial value theorem, or you can write f of 0 is equal to limit z tending to infinity f of z. Okay. Next we will prove final value theorem. Final value theorem on Z transform. Final value theorem on Z transform. What is final value theorem? Suppose you have a Z transform of this term, you can write if Z transform of f of n is equal to f of z, then limit z tending to 1 z minus 1 into f of z is equal to limit n tending to infinity f of n. Or you can write this to be f of infinity also, you can write with the same as f of infinity. This way also you can write the final value theorem. Okay, so here this is the term we have. We prove this result. Okay, in the same way we are taking this result, that is we are taking the limit term z minus 1 value. We are taking f of a definition. From the definition we will prove this result. Okay, so first we will write Suppose we write Z transform of f of n. What is Z transform of f of n? Summation n is equal to 0 to infinity f of n Z power minus n, isn't it? But here to prove this result, we take the Z transform of f of n plus 1. You have to remember this, okay? F of n plus 1, because Z minus 1 we have to prove it, no? So we have to take f of n plus 1. You have to take Z transform of this function, which is equal to summation n is equal to 0 to infinity f of n plus 1 into Z power minus n. So this term can be written as, when you substituting, n plus 1 is equal to m. Okay, so when n is equal to 0, here limits you have to find out. When n is equal to 0, m is equal to 1. 0 plus 1 is 1. When n is equal to infinity, m is equal to infinity. So this term becomes summation m is equal to 1 to infinity. N is equal to 0 is replaced as n is equal to 0 to infinity is replaced as m is equal to 1 to infinity. F of n plus 1 is replaced by m. Z power minus of this n is replaced by, from this n is replaced by m minus 1. So Z power minus of m minus 1 you can have. Or you can write this term to be summation m is equal to 1 to infinity f of m Z power minus m into Z. Or isn't it? Z power minus m into Z. Or you can have this Z is taken outside. Summation m is equal to 1 to infinity f of m into Z power minus m. But here 0 is missing, isn't it? Z transform definition is 0 to infinity. So we had to add and subtract one term. Summation m is equal to 0 to infinity f of m Z power minus m minus f of 0 is subtracted. Okay, because added term is added in this summation and subtracted term you have to write as it is. This term can be written as Z into f of Z minus f at 0. This is the result Z transform of f of n plus 1, isn't it? But we have to prove this result. We have to prove this result. Limit Z tending to 1, Z minus 1 f of Z is equal to limit n tending to infinity f of n. We have to prove this. For this, to achieve this result, we take this right hand side. Okay, we take this right hand side value. In this result, we take this right hand side value. Is it transform? Is it? You can write this to be. You take Z inside and write Z into f of Z minus Z into f at 0 is equal to Z transform of f of n plus 1. You can write this. Okay, we first write this one, and Z transform f of n plus 1 is in this side. And then from this you have to subtract one Z transform of f of n. That is Z transform of f of Z. Not Z transform, this is Z into f of Z minus Z into f at 0 minus you are subtracting on both sides of Z transform of the function f of n. You can write this to be, this is Z transform of f of n plus 1 minus Z transform of f of n. Or this is f of Z also you can write, or we will write this in the next step. Okay. This is f of Z. We are subtracting on both sides. This term can be written as Z transform of f of n plus 1. And what about this? Z transform of the function f of n, isn't it? Okay. Now here this side, here you have f of Z is common for both the terms. So we have to take f of Z outside. What about remaining Z? And here you have minus 1. So Z minus 1 into f of Z minus Z into f at 0 is here. Okay, minus Z into f at 0 is here is equal to this term. And here we have to apply the definition for both the terms. Summation n is equal to n is equal to 0 to infinity. What is the transform of this function? Is a transform of this term and this term. So you can write this combined, you can write summation n is equal to 0 to infinity f of n plus 1 minus f of n z power minus n. Isn't it? Both the terms are z transform of f of n plus 1 minus z transform of f of n. Since z transform is linear, you can write z transform of f of n plus 1 minus f of n as z transform of f of n plus 1 minus f of n. This way you can write, and here for this you are applying the definition. Okay. So this is the term we already have. And then if from this you can write this term to be limit z tending to 1 on both sides. You have to take limit, because this is the result, we have to prove it, isn't it? Limit z tending to 1, we have to prove this result. So further to achieve this result, we are taking limit z tending to 1. After these steps, you have to take limit z tending to 1, z minus 1 into f of z minus limit z tending to 1 z into f of 0 is equal to, you have to expand this series. Limit z tending to 1, we have to expand this series now. Okay, when you expand n is equal to 0, you have, when you put n is equal to 0, you have f of 1, isn't it? Minus, here when you're substituting n is equal to 0, it have f of 0, plus n is equal to 1, we are substituting, and 1 plus 1 you have a 2, minus n is equal to 1 is substituted, f of 1, plus n is equal to 3, when you're substituting n is equal to 2 here. Okay, so f of 2 plus 1 is 3 minus f of 2, isn't it? When n is equal to 2 was substituted, plus etc, plus n is equal to we had to take this to be here n plus 1 we are taking up to n plus 1 terms we are taking. Okay, so this term can be written as plus etc up to infinity it have, and taking z transform of 1 minus n z limit z tending to 1 is substituted here. Okay, when you're substituting z tending to 1 here, this side it becomes f of 0 alone, isn't it? Limit z tending to 1 z minus 1 into f of z minus f at 0 alone you have. When you're substituting here z tending to 1, this expansion alone we have f of 1 minus f of 0 plus f of 2 minus f of 1 plus f of 3 minus f of 2 plus etc up to infinity you can have. But for this term, you can write this term to be, since it is, we make finite to this term. Okay, we make finite this. So for this you can write limit n tending to infinity, because this goes up to infinity now. So n tending to infinity, when you're writing them as n tending to infinity, it can have f of 1 minus f of 0 plus f of 2 minus f of 1. Okay, plus, sorry, not minus, yes, minus, and here you have f of 1 plus f of 3 minus f of 2 plus etc, plus what about the last term? We make it to finite here. So here n plus 1 minus f of n as it is have. Okay, so this term here f of n plus 1 minus f of n is as it is, because n tending to infinity you can both the terms arise. Okay, which is equal to, when you're taking like this, you have f of 1 get cancelled. Okay, and this f of 2 and this f of 2 get cancelled, and here f of 3 get cancelled, and up to this f of n also get cancelled with the previous f of n minus 1. All the terms get cancelled except this f of 0 and f of n plus 1. So you have limit n tending to infinity. You can write this to be f of n plus 1 minus f at 0. F of n plus 1 minus f at 0. Okay, so which is equal to, you can write this to be limit f of n is substituting n is equal to infinity here. N plus 1 is also infinity. F of n is, when you substituting n is equal to infinity here. Infinity plus 1 is also infinity. Just we writing n itself, both one and the same. So we rewrite this to be limit n tending to infinity f of n. Instead of n plus 1, we are writing f of n minus, there is no n term here. So limit n tending to infinity f of 0 is just f of 0. So limit n tending to infinity f of n minus, this term becomes f of 0. What about your left hand side? Limit z tending to 1, z minus 1 into f of z minus f at 0 is equal to this. Here minus f at 0 minus f at 0 get cancelled, and we achieve the required result. Limit z tending to 1, z minus 1 into f of z is equal to limit n tending to infinity f of n. This is our final value theorem on z transform. This exam point of view, initial value theorem and final value theorem are very important. That's all for this video. Thanks for watching. Thanks for your time. And if you have any doubts in this, please provide in the comment section. Thank you.